We present a computational framework to simultaneously optimize design and manufacturing objectives for fiber-reinforced composites. In traditional pipelines, topology, structure, and manufacturing process are optimized separately in two phases. Mechanical strength optimized in the design phase is often sacrificed in the manufacturing realization phase. Differently, we simultaneously optimize both the design and manufacturing requirements to achieve the improved performance of 3D printed fiber-reinforced composites. Our co-optimization pipeline is based on three implicit neural fields, which include a density scalar field for topological structure, a material deposition field for manufacturing layers, and an auxiliary field to help define the fiber directions. Finite element analysis is employed to evaluate the mechanical strength according to Hofmann criteria in the loop of optimization. Using backpropagation of neural network-based self-learning process, we can minimize a loss function with integrated design and manufacturing objectives. The optimization is conducted in iterations so that the structural topology, the curved layers, and the fiber orientations are jointly optimized. After extracting the solid model and the orientations of fibers from the implicit neural fields, an optimal setup orientation for manufacturing is determined. We then construct the support structures for the solid and generate toolpaths on every curved layer. Here shows the comparison with a method using two-phase optimization for design and manufacturing objectives. In the first phase, topological structures and fiber orientations are optimized. The manufacturing constraints are then imposed to optimize the printing layers in the second phase. The mechanical strength optimized in the first phase is sacrificed in the second phase for ensuring the manufacturability in 3D printing. In contrast, our method can simultaneously optimize the design and manufacturing objectives together. As a result, 23% improvement in the maximum yield-free load can be achieved. As shown in the Hofmann criterion distribution, the result of two-phase optimization gives a much larger yielded area when applying the same load. Our method can incorporate manufacturing constraints for motions in different degrees of freedom, supporting 3D printers with 5-axis motion, 3-axis motion, and also planar layer-based motion. Here shows the printing process of the GE bracket model by using motions in different degrees of freedom. Here shows 4 results for the GE bracket model. 2 models are generated by different optimization approaches for 5-axis printing. Our co-optimization approach can achieve 33% improvement in the failure load. We also generate 2 other models, one for 3-axis printing and the other for planar layer-based printing. Compared to the other methods in literature, our method integrates design and fabrication objectives into a unified computational process that directly formulates the anisotropic mechanical strength and the manufacturing constraints of fiber 3D printing into topology optimization. The optimization result for fiber-reinforced thermoplastics with high mechanical strength has been verified by physical fabrication using multi-axis 3D printing with different motions. Thanks for watching.